Welcome to this model. In this model, we'll be looking into bioamplifiers. Generally, biological signals have low amplitude and low frequency. So, to increase the amplitude level of biosignals, amplifiers are used. And the output of these amplifiers are used for further analysis, and they appear as ECG, EEG, or EMG signals. So, such amplifiers are called biological amplifiers. And the basic requirements of bioamplifiers are the biological amplifier should have a high input impedance, and it should have isolation and protection circuits, and it should have constant gain and a small output impedance, and the bioamplifier should be free from drift and noise, and the common mode rejection ratio should be greater. These are the types of bioamplifiers: differential amplifier, operational amplifier, instrumentation amplifier, chopper amplifier, and isolation amplifier. And differential amplifier and operational amplifier operating in differential mode can be used, whereas output voltage is given by V0 is equal to AD into V1 minus V2. And this is the diagram of a differential amplifier. And the circuit is just a combination of an inverting and non-inverting amplifier. V1 and V2 are the voltages applied at its inverting and non-inverting terminals. AD is the differential gain. And as per the equation, the output of this OpAmp must be 0 when the voltages applied at its terminals are equal to each other. And hence the output voltage will be equal to the sum of the output voltage produced by the OpAmp, and the OpAmp circuit operating as a non-inverting amplifier. Thus V0 is equal to RF by R1 into V1 plus V2 into RF by R2 plus R3 into 1 plus RF by R1. So lastly, if we equate, V0 is equal to minus RF by R1 into V1 minus V2. That is, output voltage is proportional to the difference between the two input voltages V1 and V2. OpAmp is the multi-stage amplifier in which a number of amplifier stages are interconnected to each other in a very complicated manner. Its internal circuit consists of many transistors, FET, and resistors. So it is packed in a small package and is available in the IC form. The term OpAmp is used to denote the amplifier, which can be configured to perform various operations like amplification, subtraction, multiplication, addition, differentiation, and integration. So this is the symbol of an operational amplifier. It has two input terminals, inverting and non-inverting terminal, and one output terminal. And the two input terminals form the differential input. And the terminal with the negative sign is called as inverting terminal, and the terminal with the positive sign is called as non-inverting terminal. And if you apply an input signal to the inverting terminal, then the output signal will be 180 degree out of phase with the input signal. If you apply an input signal to the non-inverting terminal, the output will be in phase with the input signal. So these are the ideal characteristics of an OpAmp. The ideal OpAmp should have infinite voltage gain, infinite input resistance, zero output resistance, infinite bandwidth, and zero noise. It should have a zero power supply rejection ratio and infinite common mode rejection ratio. And the next type of amplifier is instrumentation amplifier. In biomedical applications, high gain and high input impedance are obtained by using the instrumentation amplifier. Usually, three amplifier setup forms the instrumentation amplifier, and the output of the transducer is given as the input of the instrumentation amplifier. Before the signal goes to the next stage, the special amplifier is required with a high CMRR, high input impedance, and to avoid loading effects. Such a special amplifier is called an instrumentation amplifier, which does all the required process. So the figure shows the instrumentation amplifier. To each input of the differential amplifier, the non-inverting amplifier is connected. So as you can see in the figure, the amplifier on the left side acts as non-inverting amplifier, and they are combined together to form the input stage of the instrumentation amplifier. And the third amplifier is the differential amplifier, which is the output of the instrumentation amplifier. The output from the difference amplifier Vout is the difference between the two input signals given at the two input points. V01 is the output of OpAmp 1, and V02 is the output of OpAmp 2, and Vout is equal to R3 bar 2 into V1 minus V01 minus V02. And the next is isolation amplifier. It is an amplifier which increases the input impedance of the patient monitoring system. It helps to isolate the patient from the device. So using this isolation amplifier, it prevents accidental internal cardiac shock, and it provides 1000 ohms insulation between the patient and the power line in the hospital. Figure shows the isolation amplifier. Here the input is supplied to the amplifier and then it is given to the modulator, and the output of the modulator is connected to a LED, and the output of LED is connected to a photodiode, and the only connection between the LED and photodiode is light signal. So the output side is separated from the input side, and in the output side the output of the photodiode is connected to demodulator and amplifier. The final output is taken. So the electrical signals are obtained with the electrodes, and the signals are received then goes to amplifier block where amplification occurs, and after amplification the signal enters into modulation block, and it goes to isolation barrier. Either a transformer or a LED and a photodiode can be used. So finally the amplified output demodulated signal can be obtained without giving shock to the patients.